So thanks for the introduction, Chris. I always love being here and addressing this particular conference. And today I'm going to talk about predicting crashes using symmetries in physics. Um, but actually, before I start, I must I want to dedicate this talk to Peter Carr, who we lost on March 1st, 2022. He is a great legend in the field of options pricing and is a crucial contributor to this particular research on the use of symmetries in options pricing. He's personally a great mentor and friend.
I
And
know him. He's a great guy, and he has
yeah,
done seminar work, and we covered him in one of the other events. Thank you.
yes, yes. And he was an advisor to FMI Tech as well. So he contributed a lot to this particular research. The first time I presented it was at NYU at his Brooklyn conference. So it's a little bit emotional this time for him, but yeah, I dedicate this particular talk to him. And with that, I'll get started. So first, I'll talk about what are bubbles and crashes, and how do we kind of predict them. But even before that, because this is an AI conference, I'll talk about why AI actually doesn't work that well here. More than 80% of AI-based hedge funds in the last 10 years have shut down, as per Bloomberg, and usually taken down by some kind of market correction or crash or flash crash. And the reason AI is not able to deal well with the crashes are that they cannot deal with the small sample sizes and non-stationarity inherent in financial markets near criticality, which is where crashes often happen. And they kind of overfit to the in-sample data, and it's hard for them to kind of detect a crash when probably it has not occurred in the data which they have fit. And because it's a black box, you can't kind of like diagnose it. You don't have analytical control over it. And yeah, it's also often unusably slow if you want to backtest it and so on. So I won't mention AI after this slide, and apologies to Chris and others. You guys love AI, but we'll deal with the alternatives in this approach. So to forecast or predict crashes, you need top-down or analytical models. Unfortunately, physics provides a whole lot of these. You know, so one is the Johansen-Lader Sornette model, which was developed in 1998, which we'll talk a bit about. Then there is the early warning signals models, which have been developed by Guttel et al. Based on like dynamical systems theory. And people have investigated cross-sectional dependent structures as precursors to crashes, and there are people like Rafael Duardi and others who have worked on this. And the approach that we will kind of favor is critical phenomena out of equilibrium, treating crashes as kind of critical phenomena or as a non-equilibrium CFT. So there are similarities in this approach and the Sornette model, which also treats them as critical phenomena, but that doesn't apply the tool of non-equilibrium conformal field theory. And we'll see what kind of leverage that actually buys us here. And in a sense, all of these, in some explicit or implicit sense, these methods rely on finding symmetries, or in the financial time series, or some kind of group theory. So we'll talk about a bit about that as well. So before we start, we just want to distinguish exogenous versus endogenous crashes, which belong to completely different dynamical classes. And one can see this by looking at the volume profile or the volatility profile of these crashes. Crashes which are endogenous in nature, which are kind of caused by the internal dynamics of the market, they have a more symmetric structure. So a more symmetric increase, power law increase in the volume or volatility leading up to the crash, and more or less the kind of symmetric decline after that, with similar scaling exponents. However, exogenous shocks usually characterized by highly skewed volume increments. So volume spikes suddenly, some big news event has come out, and then it declines gradually. So any method that wants to predict crashes can obviously only predict endogenous crashes, cannot predict exogenous shocks. For instance, the COVID-related shock in March 2020, no algorithm could have seen it come. So that naturally has no early warning signals, but those crashes have kind of like after effects, or the market, the way in which the market responds to that can be captured using some models, and we can talk about that. But for the most part, we will be engaged in predicting endogenous shocks to the market, or endogenous crashes. Um, and these endogenous crashes are actually usually caused by irrational exuberance in the market, which is some kind of a market bubble, when the observed price trajectory deviates from its intrinsic fundamental value. So the price is driven up usually by sentiment. It doesn't reflect value. And this, for instance, happened in the dot-com bubble of the early 2000s, the housing bubble of 2008, and recently the inflationary bubble of late 2021. And what happens is when liquidity starts to dry, banks start raising rates, capital inflows stop, and usually there occurs a panic synchronized selling, causing the bubble to pop. And when the bubble is nearing the point where it's going to pop, the market becomes kind of unstable, like a ruler balanced on the tip of a finger. And then even small shocks or small synchronized sell-offs can trigger a whole avalanche and cause the market to crash. And this phenomena is a symptom of criticality, or critical phenomena in general, which are accompanied by some kind of scaling or conformal symmetries, as we've seen in different areas of physics. We see these in phase transitions, in fluids. We see them in the dynamics of the early universe, and we also see them in magnets, and in earthquake dynamics as well. On the onset of earthquakes. So, I mean, these scaling laws, these critical phenomena are actually widespread across physics, and usually before the crash happens, and you have a bubble, it is characterized by power law growth in the price as opposed to exponential growth in the price. Usually, capital in markets grows exponentially due to compound interest. P dot is proportional to P. But in markets where you have a lot of positive feedback, where the participants are kind of imitating each other, or they're herding, they're following the herd mentality, P dot is usually proportional to P to the power some alpha, and rates, the price grows much faster than exponentially, and the bubble forms, which is characterized by power law growth, and it kind of fuels itself, uh, and it eventually becomes unsustainable, and then results in a finite time singularity in the model, as we've seen in multiple cases. I mean, the example I've put here is 2013 Bitcoin bubble, but you can see this in lots of different bubbles. So, we've kind of defined, very basically given some intuition about what a bubble is, what a crash is, and how to think about it mathematically. So let's think of some approaches to, forecast these, or to detect these bubbles and try to forecast these crashes, see if they work or not. So one method is the early warning signals, that kind of literature, which is based on classical dynamical systems models. They're similar to the non-equilibrium skew model introduced by Igor Halperin, as well, which is actually the quantum version of this classical model. You're basically dealing with NSD, with the noise term, and then with the drift term, which corresponds to a double well potential, right? So it has a constant term, then a linear term, and then a cubic term. So what this actually corresponds to in terms of the double well potential is something like what you see actually below in the figure, where you have this potential with two wells, and probably the metastable state is the well on the left, which is not so stable, and if you kick the price out too far, it will fall into the stable state, which will correspond to the crash in this case. I mean, you know, yeah, and then in this case, if you look at the orientation, the price is moving to the right is positive, but usually for crashes you want price moving to the left, but the idea remains exactly the same. So based on these dynamical systems models, people like Vishesh Guttal and others actually came up with these early warning signals of when the potential becomes more and more unstable, what do you expect to see? So as the metastable state kind of moves from what you see on the blue to the orange to the green, it'll correspond to basically increasing volatility of the returns. It can correspond to increasing autocorrelation in the returns at lag one, which is kind of like critical slowing down, because price disturbed from the equilibrium will take kind of longer to now come back to equilibrium, and it can give rise to increasing skewness, which will happen because of the fact that now the minima is asymmetric on both sides. So you'll have the negative moves that are closer to the crash will be a bit larger than the positive moves, which take you away from the crash dynamics. So all of these things can be kind of visually seen, and it's actually be decreasing skewness in the case of the crash, of the actual crash. So you can see this from here, and the weakness of this model is that the results are classical. They may not hold under quantum or stochastic corrections, which basically corresponds to large noise, and then also they rely on a specific SDE, which is a non-disordered SDE, whereas markets you expect disorder. So there are some pros and cons to this approach. In the end, we'll have some graphs to see if any of these tests actually work to predict the recent market correction which you've seen. Okay, but here, I mean, this is just the motivation, and it seems like the approach seems kind of promising, but there are weaknesses here. Okay. The other approach you can use is maybe use network effects. You will use correlation matrices between stocks. They'll come up with the graph theoretic representation of these, and then from that they'll measure market-wide contagion on the basis that a lot of trading before crashes will be through ETFs or through joint channels. Weaknesses of this are many. Relies on linear correlation. It works only on market-wide crashes, and the theoretical ground holds just for exogenous crashes in any case. So maybe network effects will not be so interesting for us here. Do symmetries work in predicting crashes, or like some kind of group theory? Will that work? And to answer that question, I'll give you a crash course in group theory. This is something I've given before at this conference, but I'm assuming that we have a bunch of new participants this time. So I'll kind of give it again. And please feel free to interrupt me at any time to ask questions. Symmetry groups are really fundamental in finance, since you expect investor to behave the same at kind of neighboring points in time or time scales. And what is a symmetry group? It's just a set of possible transformations that leave a system unchanged. If you look at this triangle, you can keep like rotating it, and that will leave it unchanged if you rotate it by 120 degrees and so on. And then you can kind of flip it around. You can reflect it, and it can shape remain unchanged. So these rotations and reflections together form a group of 6 possible transformations, which you see below. And yeah, that's just basically what a symmetry group is. And there's a motivation for the symmetries group in symmetries approach in physics, because Sasha Polyakov had a dream to do away with basically path integrals and SDs and solely characterize dynamics in terms of symmetry groups, which launched the conformal bootstrap program, which is highly influential in physics. But then there's also motivation for using symmetries in finance, because time translation invariance and log price translation invariance are common assumptions in almost all canonical models for options pricing, which you see, or equities dynamics for that matter. And self-similarity of prices, which is the symmetry we are kind of more interested in here, has been known since the time of Malder-Brough. To notice it for cotton prices, and the logic was that investors at marginally different time horizons behave in a similar way. And yeah, and we know theoretically that RG flows often end in self-similar fixed points as well. So you expect to see self-similarity in certain regimes in the market, just because the market undergoes renormalization group flows. And you can also expect dynamical phase transitions to be characterized by self-similarity, which is this scaling symmetry. I use the terms interchangeably. And then the third motivation is actually one that's kind of the most relevant for this talk, which is that Johansson, for instance, he modeled crashes using these multi-agent icing models, and with the local investor interactions and global interactions through the media. And then from this he actually derived these log periodic power law signatures that, in his opinion, precede crashes. And that's one use of kind of like symmetries to predict crashes, which is what we actually want. And Johansson and Sornette actually looked at this for a lot of historical crashes, 1929, 85, 87, up till 98. I mean, there are others also that they looked at more recently, and they find that kind of this model kind of fits the dynamics before the crash, fits this log periodic power law, where you have which is just a power law with complex critical exponents, where the real part will govern the power law increase, and then the complex part, if you take the real part of this whole thing, the complex exponent beta, it will correspond to basically some kind of a periodic signature, which is a log periodic signature, which means that the fluctuations will get more and more frequent before the crash. So this is a nice model. It's well motivated using multi-agent models. It has very nice looking precise prediction, but it still has some problems, and it still needs to kind of be enhanced with the conformal field theory approach, and we'll talk about this when we get back to crashes. For now, we're just exploring what symmetry groups are, what Lie groups are, what Lie algebras are, and just motivating that. So a Lie group is basically a group that is also a smooth manifold, such as the multiplication map and inversion map are smooth. These are just mathematical definitions. Lie algebra is just basically a representation, or you can think of it as a representation of a Lie group, or as an embodiment of the Lie group, which is solely characterized by the commutation relations, or by the failure of the operators to commute, which fully kind of characterize that. So just forget about the math terminology, and you can just remember that, okay, what we're going to do to constrain dynamics is, you start with the Lie group G, then you write down the Lie algebra, and then you just characterized by these computation relations, and then you write down a representation of the Lie algebra in log price times space, and then you impose that your observables are invariant under the action of these representations. And that way you can constrain different observables in your theory or in the dynamical system that you're studying, which can be expectation values, which are just 1-point functions, or you can constrain 2-point density functions, or 3 or higher point density functions, entropies, etc. Lots of observables can be constrained using these groups and their algebras and the representations of those algebras, which I mean, still now, I mean, the discussion on groups has been quite abstract. So we start with the complete abstraction. We just write down some commutation relations. We actually come up with these operators, G, P, H, C, and then we write down all the ways in which they don't commute with each other. And then basically this forms the Lie algebra of the Schrodinger group, SH2. And these are just symbols for now. You don't need to know, they don't mean anything yet. However, if you identify these symbols with what they're doing to price and time, you get that by identifying them in this particular way, you will get back these commutation relations. So how what these symbols now correspond to here is that the time translation will shift time back and forth, log price translation will shift log price back and forth. The boost will kind of rotate the time and price axis relative to one another, and expansions and dilatations will together zoom in and zoom out the price and time, where time is zoomed in or out twice as fast as price here. And so each of these symbols is actually doing something to price or time, and you want your system to be invariant under these actions of price and time for your system to obey that particular symmetry group, or that the algebra corresponding to that Lie group. And there's a very nice exercise one can do by imposing log price and time translation invariance and constraining options pricing density functions in this way. We are not interested in options in this talk, so I will not spend much time on these. But in the previous versions of the talk, where we're interested in actually constraining option pricing functions, we actually use these groups, and we apply them on these different density functions, and we get our Black-Scholes and nonlinear deformations of Black-Scholes and so on. And we find that in fact the Schrodinger group is not enough to get Black-Scholes. We need an infinite dimensional group, which is the higher spin group, to kill all the nonlinearities, to kill all the arbitrage in this theory. And again, all that is not so interesting. Now, what's more interesting is because we're interested in crashes, right? How about we try to come up with a group that describes markets during times of crash? So during times of crash, we empirically observe that time and price scale uniformly. So market is invariant under time and price kind of being scaled by the same factor lambda, which means that your Hurst exponent, which was 1/2 earlier, now goes to 1. And in fact, this is a point of enhanced symmetry, which is called the 2D conformal group. And we see that there are two ways of getting from the Schrodinger group to the 2D conformal group. And one is setting volatility, or sigma, which corresponds to volatility, to infinity in your Black-Scholes or Schrodinger like dynamics. And the other is kind of through a third group, which we'll see soon. So before that, let's talk about the 2D conformal group, and what are these conformal symmetries that arise during crashes. So in complex coordinates, you can package log price and time into this complex exponent z, and then the commutation relations of the 2D conformal group simply form the what we call the Virasoro algebra, which is actually given here. Ln and Lm are equals n minus m of Lm plus n. It's an infinite dimensional group. And the infinitesimal conformal generators are actually given by this particular form, minus z to the n plus 1 partial derivative of z. And from this form alone, you can get a lot of familiar symmetries, like, for instance, setting n to minus 1, you get time and price translations both together. And setting n equals 0 here, you get scaling and Minkowski rotations here. And n equals 1 will lead to special conformal transformations and so on. So you can basically get your familiar kind of symmetries from this, but you also get a lot more symmetries, in fact, infinite number of symmetries when the market is about to enter a crash, or when the market is actually crashing, and when it's conformally invariant and does not obey the Schrodinger or Black-Scholes dynamics, right? And again, this is the part where you constrain your options pricing density functions using this. We're not so concerned with options, right? So, I told you there's one more way to get from kind of from Black-Scholes to conformal or from to crash dynamics, and that's through this third group called the Liftshield group, right? And here you introduce a different kind of scaling to reproduce factors which you see. You scale log price and time in an inhomogeneous way, where the scaling exponent, where the system is invariant under x going to lambda x and t going to lambda to the z times t. Now, z equal 2 would have described Black-Scholes, z equal 1 would have described conformal markets, but here you are interested not in either of those two, but in z being another variable, which will actually realistically be dynamical. So it'll be a function of time, and then in your model, then you can take z from 2 to 1, and then that dynamics will describe your normal market regime then going to a crash. And this can describe endogenous and exogenous crashes. So the group has really simple commutation relations. It just has dilatations, time translation, and log price translations. So again, you can constrain density functions, write down PDs, calculate 3-point functions, whatever you want. You can do all of that. We're not interested, but yeah, the basic point is that you can get from Black-Scholes to conformal markets using two routes, either the Lifshitz group or the infinite volatility limit. And yeah, you get to the same point. So now that we know that you can use symmetries in theory now, at least, to get from a normal market to crashes. Now you can explore basically let's talk a bit about maybe having a weaker form of scale invariance, and this will get us back to the Sornette model, where you have invariance under x to lambda x, where lambda is actually kind of like discrete, and this is actually motivated through Ising-like models of investor interactions. We talked about this, where they interact locally through networks and globally through news. So at criticality, basically all investors will kind of behave in the same way, and as the global effects completely dominate, and you can get something similar to basically a scale invariance after that. So this model is actually the log periodic power law model of Sornette, which starts with an SD. That's how he motivates it, where you has this DJ term that quantifies when the crash happens. J equals 0 before crash, equals 1 after crash. Kappa quantifies the amplitude of the crash when it occurs, and basically the hazard rate quantifies the probability of the crash. So the expectation or value of DJ is given by some hazard rate times dt. And now coming back to the discrete scale invariance before, he argues that this hazard rate must be scale as a power law with the complex critical exponents. And if you actually write this down, expand this, you get the scaling law with the power law on one side, and then the power law with this log periodicity as being the other term. So you have all these parameters, alpha, beta, omega, phi, and tc, and you feed this into the expectation value of the price or the price change, and then you can get you can integrate it to actually get the expectation value of the log price before a crash, which is given by this particular form, which is the log periodic power law form. And in the CFT literature, this is just a non-unitary CFT with complex anomalous dimensions. But I mean, this is really messy to fit. This is really messy. It has 7 parameters. And as von Neumann says, with 4 parameters, I can fit an elephant, and with the 5th, I can make his trunk wiggle. So there's an analysis done that shows that this has, yeah, please. Yeah, you're saying something, Chris?
Yeah. I was saying you may try to conclude.
Yeah. So I was saying this can easily lead to overfitting. So this is not necessarily the best possible model, but this is the punchline of the talk, actually, that you can use CFTs for prediction purposes, and CFTs come from basically from the intuition of the dynamical fractals. And but what you're doing now is that you're writing down the CFT in 1 dimension rather than two dimensions. So you're promoting log price from a dimension to an operator, and you get this power law scaling. You take the logs of the 2-point functions. You get that basically a time varying anomalous dimension can be related to the time varying Green's function here, right? And you can add multifractality if you have nonlinearity. The calculation is exactly the same. But the idea is that this is very general. You can have non-stationarity, nonlinearity, and even break conformality by giving different kinds of dependence to the critical dimension. But now the point is that this anomalous dimension will tell you when a crash is going to happen. So it will actually start to trend up, or the trend in the anomalous dimension will be positive before bubble-induced crashes. And for 50 most liquid stocks in the S&P 500, we see in the last year the inflationary bubble-induced crash. So in the blue is the trend in the anomalous dimension before the crash. In the yellow is the trend at other times, the average trend at other times. You see that mostly the trend is roughly equally positive or negative, but right before the crash, you have a very strong positive trend in the anomalous dimension. That's the punchline of this talk. And there's none of the other signals have such a nice positive trend before the crash, whether it's the Kendall trend of lag 1 autocorrelation, kurtosis, instantaneous frequency. And in fact, the trend of skewness has a positive trend before the crash, whereas the early warning signals literature predicts a negative trend. So it's interesting that the early warning signals are anti-predictive in that sense. So that's basically the punchline of this talk, and we talk about exogenous shocks next time. So the only conclusion is that AI/ML, Sornette models, early warning signals have many limitations while forecasting crashes, but the CFT work solves a lot of their problems, and it's not just a nice theory for crashes, but also works very well in actually predicting these market crashes. So that's basically where I am. And yeah, thank you.